Swayam Prabha, free DTH channel for education.
I can write here. This is going to become like k y2. I can write it. This is going to be y2, and this is going to be k y2 dash, and this is going to be y2 dash. Okay. So in this case, it is going to become like k. I can take it. So this is going to become like y2 dash minus y2 dash is going to come. Okay. So minus k into y2 dash is going. Both are going to become 0. Therefore, this is going to be 0. On the other hand, you can write this way also. Okay, I'm going to write here. So this I can write as c y1 into c y1. Okay, y1 dash into c y1 dash I can write it. So in this case also it is becoming like c y1 dash. Okay, c y1 dash. Okay, minus c y1 dash is going to come. So I can write cancel this. This is going to come. Okay. Therefore, what you get, you are going to get this as 0 all the. So you can find the Wronskian of these functions and then you can verify that. So already I did one problem x cube x square, we have done that already. So you can do this as an exercise. Okay. Next one, we are going to see when the solution is going to be obtained. Okay, p of x and q of x are continuous functions on some interval a b. Then we are going to see when this solution is going to obtain. Okay. So we are going to consider this problem. So let us consider this problem. P of x and q of x are continuous. Okay. So let's take this problem y double dash. Okay, I'm going to consider this problem y double dash plus p of x into y dash plus q of x equal to 0. Okay, I'm not going to consider the non-homogeneous part, only homogeneous part I'm going to consider. And I have y of x not equal to y naught and y dash of x not equal to maybe I'll put it k naught and k1. Okay, it's not y naught and y1. So let me put it as k naught and k1. Okay, so this is the initial value problem. Okay, then the following theorem is saying is that if p of x and q of x, suppose this p of x and q of x are continuous, p and q are continuous. Okay, in some interval. In some interval where that x naught is going to be in that. Okay, where x naught is also in that interval. So it is continuous on some interval a b and x naught belongs to a comma b. Then this IVP has a unique solution. So this theorem is saying this IVP has a unique solution. Okay, I'm not going to prove this one. This is beyond the scope of this syllabus. So if you want to take it further, you can just verify. You can, if you are interested in reading the proof of this theorem, you can refer this book, Ying's book, Ordinary Differential Equations. Okay, there you can see the proof of this theorem. Okay, now what we are going to see. The linear dependence and independence of solution. What is the linear dependence and independence of this solution that we are going to see? So this we are going to see now. Okay, suppose y1 and y2 are two independent solutions of this equation on some interval a b with x naught belongs to a b. Then any solution, suppose this is that, then any solution y. Okay, suppose there is another solution in form, then that solution can be written in the form alpha y1 plus beta y2. Where alpha and beta are some constant. Okay, you can find some alpha and beta such that alpha y1 plus beta y2 equal to 0. Where alpha and beta are real numbers. Okay, and if S denotes the set of all, suppose S is denoting the set of all solutions. Okay, set of all solutions of this equation. Okay, or let's say this one. Okay, solutions of one. Then what we have is S is a linear span of. Okay, then what we can say is that S is a vector space. Means I can say S is a linear space. S is a linear space, I can say. Okay, and you can prove that dimension of S is also less than 2. Dimension is also less than or equal to 2. That also we are going to see. Okay, then the proof of this theorem I will give it at the end of the lecture. Whoever is interested, who can concentrate on this one. Whoever is not interested, you can just leave after the regular classes. Okay, so I will give the end of this proof of this one at the end of the lecture. Okay, we will just postpone that until that. Okay, now what we are going to have existence of a general solution. Okay, so what we have is that suppose this is the existence of uniqueness we have seen here. and then if some other solution is there, then it is going to say that is going to be of this form if y1 and y2 are independent solution. Now this theorem is going to say that suppose p of x and q of x are continuous on a comma b, then this problem has a general solution on a comma b. So if it is having p of x and q of x are continuous, by the previous theorem, okay, the theorem number 3 is going to say existence and uniqueness. The last theorem is going to say about the linearly independence and linear dependence. So combining these two theorems, we are going to say that this problem has a general solution, and also we can say that so what is it meaning is that the dimension of S is not less than or equal to 2. It is going to be exactly 2. That's what we are going to do. So for that, what we are going to do is that we are going to prove it with a simple logic. Suppose y1 and y2 be two solutions. Okay, y1 and y2 be two solutions of let's say 1. Okay, this or I have solutions of this ID. Okay, such that what I'm going to define is that I'm going to define, okay, this boundary condition I'm going to define this way. So first I'm going to define L of y1 equal to 1. Okay, where L of y1 equal to 0. What is L of y? This is going to be L of y. Okay, this is going to be L of y. So L of y1 equal to 0, and I have the condition that y of x naught equal to 1 and y dash of x naught equal to 0. Okay, this is first condition. Now for L of y2, what I am going to take, L of y2 equal to 0 and y of x naught. So this is the second one I am going to take, y of x naught, y2 of x naught, or put y1 of x naught, y2 of x naught. Y2 of x naught equal to 0 and y2 dash of x naught equal to 1. Okay, these are the two conditions. Then what I have is that, what I can prove is that I can prove that. So once we will use the same logic over here once you are looking out there. So here what you can do is that you can prove that w of, okay, x naught is not equal to 0. For example, w of x naught is going to become like, w is going to become like y of x naught, y1 of x naught, that is going to be 1, y dash of x naught is 0, and the y2 dash of x naught, y2 of x naught is 0, y2 dash of x naught is 1, that is 1, which is not equal to 0. Okay, therefore what you are going to get, w of x naught is not equal to 0. That means if this w of x naught is not equal to 0, this is going to form a linearly independent solutions. Okay, so therefore y1 and y2 are linearly independent, and dimension of S is already less than or equal to 2. If dimension of S is less than or equal to 2 and y1 and y2 are independent, then what you are going to get is that the dimension of S is going to be 2. So what is this theorem is saying is that the linear ODE with this setup, okay, this linear ODE with this setup, this IVP does not have a single solution at all. Okay, there is no single solution. Whatever solution we find, that can be written in this format only. Okay, that is the theorem is going to say. That you cannot find more than this one. Okay, that means it is not going to have any single solution. Okay, and then we have general and particular solution for non-homogeneous ODE. Okay, so general and particular solution for non-homogeneous ODE. How do we find that? Okay, so for this case, what we need to do is that you have to split this into two parts. Okay, first part what I am going to do is that I am going to take one part as a homogeneous part. Second part I am going to consider as a particular solution part. Okay, so first part, so I am going to consider this problem. Okay, so instead of this one, I am going to take this one equal to r of x is there, okay, equal to r of x is there. So in this case, what I have, first you got to solve this problem. Okay, first you got to solve this problem, y double dash plus p of x into y dash plus q of x into y equal to 0 should be solved. So this is going to called as y dash, which is called the homogeneous solution. Okay, and then you got to find a particular solution. Okay, the particular solution is going to be obtained for the non-homogeneous part. Okay, suppose y dash is the general solution of the homogeneous ODE. Okay, so this one. Then what you have, yp is any solution of 9. Okay, means yp is any solution of this equation on AB containing no arbitrary constants. There should not be any arbitrary constants. Okay, so that is nothing but yp I have. So suppose I have yp, which is solving this one. Okay, it is not having any it is not containing any arbitrary constants. Okay, then the particular solution of this equation is a solution obtained from 10. Then what I can get is that I can obtain the general solution of that one. So that is going to become like yh plus yp. Okay, yh plus yp is there. So this is going to be the general solution. If yh is the homogeneous solution and yp is the particular solution for this one, this is going to be the homogeneous solution, general solution for the ODE. Okay, this is going to be the general solution for the non-homogeneous ODE. So here a particular solution of 9 in AB is a solution obtained from 10 by assigning specific value. So you can assign some specific values to C1 and C2 and then you can obtain the values of VP also. Okay, that is called a particular solution. Okay. So suppose so this we are going to say the general and particular solution. Okay. So what I have is that I have y hat. So I have this y hat is going to be the general solution for this problem. So that means I can write this is going to become like C1 y1 plus C2 y2 is going to come. Okay, that is nothing but the general solution for this homogeneous ODE. Suppose we have other solution yp. Okay, we have other solution yp which is going to satisfy this one. Okay, then what you can get is that you can obtain your general solution as y equal to yh plus yp. That means suppose y1 and y2 are two independent solutions, then you can write that as C1 y1 plus C2 y2 plus y2. Here this yp is not having any arbitrary constants. Okay, here C1 and C2 are arbitrary constants are there, but in the yp part there should not be any arbitrary constants should be involved over. So this is the general solution for the non-homogeneous ODE. If you want a particular solution, what you need to do is that you can put that in the homogeneous part. For example, if I have C1 y1, in this case particular solution means I can put like 2y1 plus 3y2 I can put it, and that is going to be giving you the particular solution for the non-homogeneous ODE parts. Okay, so that is that. Okay, so the general solution of non-homogeneous ODE, again this is not without proof. Okay, we are going to okay, this theorem of the proof of this one will be provided later again. Okay, so we are going to see that. So suppose P of x and Q of x and R of x in this equation are continuous. So now this theorem is going to say that if P of x and Q of x and R of x in this ODE is continuous, okay, they are continuous, then every solution of this equation, okay, can be obtained by assigning a suitable values to the arbitrary constants C1 and C2 in a general solution. Okay, that is the this theorem is going to say. So this proof will be provided after constructing the solution by various parameters. Okay, that is going to be obtained from. Okay, that we will see. So we'll see that. So we'll see the omitted proof now. So we have given that problem now. The linear independence and independence of solution means that Wronskian etc. we will do that. So that we'll see that. Okay, the omitted proof. So suppose y1 and y2 are independent solutions of 8. Okay, the equation that what we have is the equation number 8 is as follows. The IVP. Okay, the IVP is the equation number 8. Okay, this is equation number 8. So for this equation, we are going to see what is the theorem related. Okay, suppose y1 and y2 are independent solutions of 8 and AB. If x naught belongs to AB, then any solution y can be written in the form alpha y1 plus beta y2 for some alpha comma beta in R. Suppose S denotes the set of all solutions of the IVP, then S is a linear space and dimension of S is less than or equal to. So let us assume that. So let us prove this one. So prove this as follows. So suppose y is any solution, y be any solution of, okay, the equation number 8. Okay, so y be any solution of equation number 8, and then y1 and y2. Okay, y1 and y2 are two linearly independent solutions of again the equation number 8. Okay, solutions of 8. The 8 is the equation. So the 8 is equation number 8 is this one. So we have equal to 0 here. Okay, we are not going to talk about the other things. So this is going to be that. So y of x naught equal to k1, k naught, and y dash of x naught equal to k1. Okay, this is equation number. Let's say this is 8, equation number 8. Okay, so for this one we are going to see what is the solution is going to come. So we are going to prove this theorem for this one. Okay, so by superposition principle, we know that alpha y1 plus beta y2 is also a solution. Beta y2 is a solution. Okay, since y1 and y2 are two linear independent solutions, therefore alpha y1 plus beta y2 is also a solution of this problem. Now, if you go for the next one, okay, so now we are going to consider this following system. Okay, we are going to consider this following system. Let's consider this. What we are going to do is that we are going to consider alpha y1 of x naught. Okay, alpha y1 x naught plus beta y2 into x naught. Okay, alpha y1 x naught plus beta y2 of x naught equal to k naught. Okay, because y2 is a solution, so therefore should satisfy this condition also. Therefore, alpha y1 of x naught plus beta y2 is of x naught equal to k naught is going to satisfy because y1 is a solution. Similarly, see alpha y1 plus beta y2 is a solution, so I can just substitute over here. Therefore, we are going to get that. Now, alpha y1 dash of x naught. Similarly, alpha y1 dash of x naught plus beta y2 dash of x naught also should satisfy that. Okay, y1 dash of x naught equal to k1. This should also satisfy because alpha y1 plus beta y2 is a solution. It should satisfy this one as well as this one. Okay, I am just substituting. So in matrix format, what I can write is that I can write this as y1 x naught, y2 x naught, y1 dash x naught, y2 dash of x naught. Okay, in matrix format into I can write as alpha beta equal to k naught and k1. Okay, this one I can write. Okay, so now we need to find alpha and beta. So this alpha and beta can be uniquely determined, that it can be uniquely determined. So if this determinant is not equal to the coefficient matrix, this determinant is not equal to 0, then I can find that alpha and beta is alpha and beta can be uniquely determined. Okay, so if this determinant is not equal to 0. So what is that determinant is going to be? That determinant is going to say about the Wronskian. Okay, that is going to be the Wronskian. So now let us define W of x. So W is nothing but W of x is nothing but I'm going to write it as y1 of x, y2 of x, y1 dash of x, y2 dash of x. This I am going to define as Wronskian. Okay, that is nothing but y1 y2 dash minus y2 y2 dash. Now, if you prove that W is not equal, W of t is not equal to 0, then alpha and beta are uniquely determined. Okay, if we prove that if W is not equal to 0, means if I prove that this is not equal to 0, then I can use alpha and beta can be uniquely determined from this. Then it will prove that, okay, then it proves that y can be written in the form. So this is going to prove that y can be written in the form y equal to alpha y1 plus beta y2. So that's what we are going to say for some alpha and beta belongs to 1. So and guys, what we are going to get is that we are going to get dimension of this is less than or equal to. So what is sufficient is that, so if I write yp any solution, okay, suppose I write y equal to alpha y1 plus beta y2 is a solution. So if I write this one y equal to, then what I can do is that I need to find my alpha and beta. Since y is a solution of this one, I can substitute it over here. I am going to get this one. I need to find alpha and beta. If I find alpha and beta, this is going to give me the this is going to be satisfied. So for that, now what I end up with is that this is not equal to 0. That is the only thing I got to do. Only the Wronskian is not equal to 0. So it is enough to prove that W of t not equal to 0 if y1 y2 are independent. That's what we are going to do. So the claim is here, we are going to claim more than that. What we are going to say is that we are going to say either W is identically 0, okay, or W is never 0. Okay, either W is identically 0 or W is never 0. That's what we are going to do. Now what we have W of x. So W of x is nothing but y1 y2 dash, okay, y1 y2 dash minus y2 y1 dash is there. This is nothing but W of x. Now what is W dash of x? W dash of x is going to be y1 dash y2 dash, okay, minus plus y1 y2 double dash minus y2 dash y1 dash minus y2 y1 double dash. Okay, this is going to be your W. So here y1 dash and y2 dash, these two are same, so I can just cancel it out. Okay, so therefore you are going to get, this is going to become like y1 y2 double dash minus y2 y1 double dash is going to come. But what is y2 double dash? So I can substitute it over here, okay, because I have y1 and y2 are two independent solutions. Therefore from here I can write that y2 double dash is going to become like minus p y2 dash minus q y2. Okay, similarly I can write y1 double dash is going to become like minus p y1 dash minus q y1 is going to be. So I'm going to substitute it over here. Therefore this is going to become like, I'm going to use the y1 as it is. Okay, y1 into y2 double dash is going to become like minus p y2 dash minus q y2. Okay, minus y2 into y1 double dash is going to become like minus p y1 dash minus q y1 is going to come. So this one I can simplify. So minus p y2 dash y1, okay, minus q y2 y1 minus y2. This is going to become plus y2 p y1 dash, okay, and this is going to become like plus q y2 y1 is going to come. So these two are same, okay. So here these two are same. These two are same. Therefore, this is going to get cancelled. So we are going to get minus p into, okay, minus p into, I can write this as, this is going to become like minus p into what I have y1 dash. Okay, so this is going to be y1 y2 dash minus, okay, this I have y2 y1 dash is there. But what is y1 dash, y1 y2 dash minus y2 y1 dash? That is nothing but w. So this I can write as minus pw. So I got w dash equal to minus pw. I got it. Okay. So w dash equal to minus pw. So that I am going to use it and then going to convey something. So w dash equal to minus pw. It is again ordinary differential case, right? So some simple first order ODE. So you can just put w dash by w equal to minus p. Therefore, you can just integrate on both sides. So this is going to become like, you can just find that this is going to give you w is equal to e power minus pdx is going to come. Okay, this is going to come. So w equal to e power pdx plus some constant is going to come. So once again, I can put that as w is equal to some c into e power pdx, e power minus pdx. So now this w is going to become 0. W equal to 0 if c equal to 0. Okay, because e power minus pdx is there, e power p is never become 0. Okay, therefore only if e power this is going to become like minus infinity, then only is going to be 0. But w is integral, that is not, because minus infinity is not in our okay, or infinity is not in our, or this is going to become like unbounded. P of x is going to become like unbounded. That we cannot do. So in this case, what we are going to do? W equal to 0, c equal to 0, or e power is never 0. E power exponential will never become 0. So in that case, what we are going to have? We are going to have, so it is clear that c equal to 0 plus w equal to 0. Okay, c equal to 0 means w is identical to 0. If c is not equal to 0, okay, if c is not equal to 0, c is not equal to 0, then w is not equal to 0. Okay, that's what we have. Okay. So now what I got that w dash equal to minus pw is there. Okay. So I'm just going to find what is the relation for this one. So this is the ODE I got. Okay. W dash equal to minus pw I got it. Therefore w is going to become like, if I just use the variable separable and then integrate, you are going to get c e power minus pw is going to come. Pdx is going to come. Okay. So here w equal to 0 if c equal to 0. Okay, because e power minus p, c equal to 0 means w is completely 0, and c not equal to 0 means, okay, c power minus pdx is never 0, therefore w is not equal to 0. Okay, if c is not equal to 0, w is not equal to 0. W is simultaneously is 0 if and only if, okay, y1, y2 are linearly dependent. Okay, so linearly dependent, then we are going to say that it is going to be w is identical. Suppose, okay, first case. Suppose, okay, first part, suppose y1 and y2 are linearly dependent. Okay, then what you need to prove is that you have to prove that w is identically true. This one we have already proved, because y1 and y2 are dependent. Then what we can take is that y1 equal to we have already proved just a few minutes before. So y2 equal to ky1 you can take, or y1 equal to ky2 I can take it. And then you can find that the Wronskian. So Wronskian is going to become like 0. So it is going to become identical to therefore that part is true. Now converse part. Okay, conversely, suppose w equal to w is identical 0. That means what? That means w of x is equal to 0 for all x. Okay. Now what we need to claim is that we need to claim that y1 and y2. Okay, we got to claim that prove that. Okay, you got to prove that y1 and y2 are linearly dependent. We got to prove. So here there are two cases I can take it. Okay, one is suppose y1 equal to 0 or y2 equal to 0. Suppose y1 equal to 0 or y2 equal to 0. then obviously this is going to give me that it's going to be a linearly dependent is going to come, because if you take any set, in that if you have put 0 inside that set, that basket, then that is going to become like linearly dependent. So nothing to prove over there. Suppose y1 is not equal to 0. Okay. Now next one, what I'm going to take is that I'm going to take y1 is not equal to 0. If y1 is not equal to 0, okay, y1 is not equal to 0, that means what? There is some, okay, either y1 equal to not equal to 0 or y2 not equal to 0. So without lots of penalty, I'm going to take y1 is not equal to 0. So y1 is not equal to 0 means what I'm going to have? I have some xi, there is some xi such that y1 of xi is not equal to 0. Okay, y1 of xi is not equal to 0. Now what I have, since P is continuous and Q is continuous, the solution is also going to become like a continuous one. So you are going to get y1 is going to be a continuous solution. Okay, so since y1 is continuous, what you are going to get is that you are going to get the solution. Okay, you are going to get the solution. You are going to get the solution not only in the x side, there will be some neighborhood is going to exist. Okay, there will be some neighborhood is going to exist for that. So you can find some neighborhood C comma D where xi belongs to C comma D such that, okay, it is subset of A comma B such that y of x is not equal to 0 for all xi in C comma D. Such an interval will exist because of y of x is continuous, y1 is continuous. Okay, this is going to exist. This is y1 of x. So therefore, what I can do, I am just going to use this. Okay, so I know already w of x is equal to 0. Okay, so therefore, what I can do now, this is going to imply that I can divide this by y1 square. Okay, so this is also going to become 0. Therefore, I can write this one as y1 y2 dash minus y2 dash y1 divided by y2 y1 dash. Okay, y1 y2 dash minus y2 y1 dash divided by y1 square is going to become 0. Therefore, this one I can write it as d of y2 by y1 I can write it. Okay, equal to 0. So this implies y2 by y1 equal to constant. Okay, some k, which implies y2 is equal to k by y. That means what? y1 and y2 are linearly dependent. Okay, so that is going to prove that. This is going to prove that. This is true for all x in sigma. Okay, it is not only for xi. It is going to be true for all x in sigma. So by the uniqueness property, okay, this is going to be true for everywhere. By the uniqueness property, it is going to be true everywhere. Therefore, what you are going to get? You are going to get y1 y2 are y1 y2 are linearly dependent. So that means what this is going to say, if w equal to 0, y1 y2 are linearly dependent. So if y1 y2 are linearly independent, then w is not equal to 0. That's what we are playing. Okay. So therefore, in the above proof, what we are going to have? We are going to have w is equal to c e power minus p dx is going to come. So it's called the Abel's law. Okay, this formula is called Abel's law. Thank you.